In this video, we will be solving validate binary search tree problem. It's LeetCode 98. So let's first look at the description. Given a binary tree, determine if it's a valid binary search tree. Assume a BST is defined as follows. So here it's just saying that if we have a binary tree, so we need to look at the parent and its children. So if all of the left children are smaller than the parent and all of the right children are bigger than its parent, then we have valid binary search tree and we return true. So for this example, we return false, so this is not valid binary search tree because number 4, it's right child of this parent, which is 5, and it should be bigger, and it's not. And that's why this is not a valid binary search tree. Okay, so let's look at another example. So if we have root of 10, then left child is 5, right child is 20, and then we can have 15, 30. And let's just do binary search tree validation by hand. So the rule is, if we have a current parent is 10, so all of the left children needs to be smaller than 10, and all of the right children needs to be bigger than 10. So is 5 less than 10? It is. This is valid. And are all those children bigger than 10? So they are. And also 20 is bigger than 10, so this is valid. And let's look at the 20, so the children of this now. So is 15, so it's 30 bigger than 20 it is, and 15 it's smaller, so this is valid binary search tree. Okay, but if we change one node, let's change this guy here to be 9. So if we just look at this subtree, we would say that this is valid binary search, right? Because left child is smaller and right child is bigger than the parent, right? But we actually need to do for all of its children, right? So this is not valid because all of the right children from the current parent, which is 10, needs to be bigger, right? And we see that 9 is not bigger, it's smaller than 10, so this is not valid binary search tree. Okay, so how would we solve this problem? One way of doing this, you can have min and max values. So min and max. Okay, so initial min value would be minus infinity, and the initial max value would be infinity, right? And these values would change whether you would be traversing left child or right child, right? If you're going from 10 to left, so the mean stays the same, and you would change the max and traversing the tree to 10. And likewise, if you would be traversing, when you traverse the right children, the max stays the same, but the mean would change to its band, which is 10, right? So let's talk about time-space complexity. So for time, this is O of n. We are visiting every node in the tree, and for space is O of h, right? It's the height of the tree. Please pause this video and try to code up the solution yourself. Okay, cool. Let's do it together. So the first thing we will do is to change the arity of the function. So we will have two additional parameters. So min and max, right? Min will have initial value of infinity, and the max will be infinity. Okay, and because we will be doing recursive calls, we need to have base case. So our base case is when we don't have a root, we just return true. Okay, and if we have a node, we need to check if it's between min and max, right? So if root dot value is less than equal min value, or root dot value is greater than or equal to max value, we just return false. Okay. So if current value is between these values, we just recursively do traversal for its children, right? So we go to the left, and if we go to the left, so the min stays the same and the max is root dot value, and we visit right child, and with right child it's min is root dot val and max stays the same. Okay, let's just check all the test cases and they pass. Okay, hope this was helpful. Yeah, until next time, bye.